Good morning and good afternoon, everyone. Thank you for joining us today for the CUTRIC R&D series. My name is Vince Guglielmo and I'm Director of Innovation Initiatives here at CUTRIC. Today's session will focus on bus electrification, battery charging, powertrain storage, and grid management. Before going further, I'd like to do our land acknowledgement. I'm currently based in Hamilton, Ontario, and in the spirit of respect, reciprocity, and truth, we honor and acknowledge the lands which constitute the present-day city of Hamilton, situated upon the traditional territories of the Erie, Neutral, Huron-Wendat, Haudenosaunee, and Mississaugas. This land is covered by the Dish with One Spoon Wampum Belt Covenant, which was an agreement between the Haudenosaunee and Anishinaabe to share and care for the resources around the Great Lakes. We further acknowledge that this land is covered by the Between the Lakes Purchase 1792 between the Crown and the Mississaugas of the First Nation, of the Credit First Nation. Today, the city of Hamilton is home to many Indigenous people from across Turtle Island, and we recognize that we must do more to learn about the rich history of this land so that we can better understand our roles as residents, neighbors, partners, and caretakers. CUTRIC encourages and supports Indigenous communities throughout a number of actions. We also have a gender and racial diversity policy in place that encourages the hiring of diverse voices, maintaining racial and diversity targets, as well as building organizational awareness and education therein. Next slide, please. A few housekeeping items today before going further. You'll notice that you've been through this before, undoubtedly. There's the mute and video buttons to turn yourselves on for video and unmuting, but please remain on mute at all times unless there's questions. You'll notice the menu items. Most of you have already familiar across the bottom: participants, the chat, live transcript, reactions, and how to end the meeting. And if you click on the participants item, menu item, you'll see the list of participants today. Lastly, you'll notice that many of your names are listed as unknown, brackets me. We and everyone else would want to see your name and organization of those participating. Please hover over the unknown, select more, and then click rename. Please enter your name and organization and hit save. And that way we'll all know who's here. Thank you. So with that, we'd like to acknowledge and thank our sponsors of this series. Thank you, ABB Mobility, Nova Bus, NFI Group, Centennial College, and Transport Canada. I'd like to now show you one of our sponsor videos.
The NovaBus battery electric bus sets the standard for durability and performance, no matter what type of weather comes its way. Driving across America, the LFSE Plus vehicle has demonstrated tremendous energy efficiency, strong gradability performance, a remarkable drivability, and an industry-leading turning radius. Hopping aboard the LFSE Plus means getting the support you need to facilitate your transition towards zero emission. Our experts are there to help you integrate the electric bus seamlessly into your operations. Choosing NovaBus also means selecting a highly talented team of training professionals and tailor-made programs to meet your needs. Hit the road with the confidence that comes from being supported by a wide service network that doesn't let you down. That means getting the specialized spare parts you need quickly and 24/7 customer support that is recognized for its agility and flexibility. NovaBus, your partner for a sustainable future.
Thank you, NovaBus. So now we'll get into the activities for today specifically. The CUTRIC R&D Innovation Series is a 3-day webinar format event taking place today, September 12th and October 3rd. The objectives of this series are to highlight key projects that were recently completed through Cutric's coordination and sponsored by the Government of Ontario's $10 million fund as part of its climate change strategy in 2016. The goal of the partnership was to help move the province to the forefront of public transit research and development, supporting Cutric's founding mission to spur innovation and economic growth through the creation of low carbon and smart mobility ecosystems. To facilitate interaction between researchers and industry partners for future research collaboration opportunities or commercialization adoption, and to support low carbon and smart mobility ecosystems and the adoption in public transit by fostering innovative agendas and capacities. Specifically today, go back, Pratik. So on the 16th, which is today, we will talk about bus electrification as previously mentioned. On September 12th is our hydrogen fuel cell technology topic. And on the 3rd of October, we have the moving people, autonomous transit and cybersecurity. So with that, I'd like to start and move to introduce our first speaker. Actually, there we go. So today's agenda features Rachit Khanna, who is from ABB Mobility, and he will be our moderator today. We will introduce the other speakers as we go. Because of our tight time frame, we will avoid reading the bios. The bios are all on the event website, so I encourage you to read up on each of the speakers. But right now, I'd like to turn things over and introduce Tyler Middlebrook, manager at the Ministry of Economic Development Job Creation, to say a few words. Tyler.
Thanks, Vince. Hello, everybody. My name is Tyler Middlebrook, and I am a manager at the Ontario Ministry of Economic Development, Job Creation and Trade. And I'm super excited and glad to be here today to participate in today's seminar as part of Cutric's R&D Innovation Series. As many of you attendees probably already know, my ministry has supported Cutric and its mission to make Ontario a global leader in low carbon smart mobility technologies for heavy and light duty vehicles, advanced transit, and integrated mobility applications. I'm excited to hear about the positive outcomes of some of Cutric's 37 ministry supported projects that range from electric powertrain optimization to fuel cell and hydrogen innovations to automated driving and deep learning data transfer in smart vehicles, to cite but a few examples. Cumulatively, these projects have led to the creation of over 160 jobs in Ontario and engaged over 250 industry members in 33 academic institutions. Thank you to Cutric for inviting me to participate and hear from industry experts and researchers on the fascinating work to date and what might come next on the future of transportation in Ontario. Thank you very much. I'm looking forward to today's proceedings.
Thanks so much, Tyler. So now we'll get right into it. Let me introduce you to Rachit Khanna, Sales Manager, Fleet and Transit at ABB eMobility. I'll just give you a bit of a background on Rachit. He joined ABB in 2022, where he's responsible for sales, account management, and business development for electric buses and car customers in Canada. Throughout his career, spanning over a decade, Rachit has worked in the tire trade as key account manager, handling the largest OEM in India to handling one of the biggest retail markets in the area as area manager. Rachit started his EV journey in 2017, and he's had the opportunity to work in sales, business development, and policy aspects of the business in India. Rachit was part of the winning team and the lead for execution for the 10,000 EV tender rolled out by the Government of India, which at the time was the single largest EV tender across the globe. Rachit has an MBA in International Business and Marketing and is an active member of Cutric and promotes solutions for sustainable transportation. So before bringing Rachit on stage, I'd like to show an ABB video.
Thank you, Vincent, for those kind words. And thank you, everyone here, for giving us the opportunity to be a part of this. Thank you, Qtric. I am really excited to be here today and discuss these burning topics that we have on hand today. These are the topics that define where we go in the transit space in terms of the electrification journey. I am looking forward to today's session. So without further delay, I would introduce our first speaker, Dr. Hossein. He unfortunately could not be with us today to present, but he has a recorded session for us, which we will be playing. And I'll let it over to you, Pratik, to play that video.
Hello, everyone. It's nice to meet you all. My name is Hossam Gaber, professor at Ontario Tech. I'll be talking about fast charging stations for transportation electrification, and we'll focus on the analysis and design of fast charging station with flywheel battery hybrid energy storage platform. I would like to acknowledge members in my team, including postdocs, PhD students, masters, and research assistants. Why we need fast charging? Definitely, the transportation electrification is key for climate change, and the charging time is crucial to ensure that we really able to deploy EV with reasonable charging time for practical mobility and city and urban and rural and also highway transit as well. DC fast charging is crucial and important to support the grid resiliency and the charging infrastructure. Also, the charging power limits is very important to analyze the transit industry and to support the transit industry and to ensure that the FCS technologies are matching the EV driving profiles. Also, the integration with hybrid energy storage is crucial because battery can provide a very large energy but cannot provide such amount of power. With charging, this charging time is very limited, but introducing the flywheel and ultracapacitor will compensate the charging time as well as the power density. We would like definitely to support FCS design and optimization and control to mobilize the EV, electric bus and electric truck in view of the route and station management, and to optimize the performance with advanced control. The scope of the charging station work has these key points. Number one, we would like to design and the integration with the grid. So we'd like to design the FCS and to ensure the integration with the grid. We would like to integrate ultra-fast charging capabilities that we achieved at the later stage of the project, integrate renewable energy and even nuclear power and SMR, integrate hybrid energy storage, including flywheel, battery, and ultracapacitor. We achieve modeling and simulation and actually co-simulation with real-time simulation of FCS, achieve intelligent and optimized control design to ensure performance, high performance and optimization of fast charging modeling. Based on that scope, we developed a methodology that have been spanned and executed with our team over the time span of the project, including the understanding the requirements, design requirements, hybrid energy storage technologies, standards. We analyze the control design. We analyze the integration with the grid, how to ensure the performance. We achieve the management from the bus side and from the station side and how they communicate. We achieve design with bidirectional DC-DC converter. We achieve the modeling and simulation with different scenarios within the charging station. We achieve different component selection, sizing, optimization, and we made a small scale demonstration in the lab. We also achieved energy management with intelligent control and economical factors of the fast charging. The significance of the fast charging and ultra fast charging, eventually it really enhances the grid performance and support the mobility, reduce the peak power demand, reduce the EV charging cost, streamline the tariffs and fast charging station location and implementation, minimize the influence of large scale fast charging on the grid, optimize the size of the storage and the cost as well of implementation, and we adapt to the standards and reduce the charging time for with ultra-fast charging capabilities. Eventually, we implemented also different layers within the simulation, and those including the charging parameters, the charging method, limits, route selection, the operational table and scheduling, the bus configuration, and the interface with other auxiliary power and battery and other elements. Those include the overnight charging and the station charging like depot and the opportunity charging. And we implemented a number of strategies and we evaluated them and evaluated the performance as well. This is our conceptual design, where you can see here we have the PV with the DC converter, we have the wind, we have the grid itself, and we have the different converters for different applications such as the fuel cell and maybe battery, maybe different applications like the nuclear power plant. And we implemented those with energy management and optimization with the electronics as well. The idea here is to achieve 3 possible connections: power line, data line, and control line. And we actually achieved the modeling and simulation based on the battery, flywheel, and ultra capacitor. For the flywheel, we actually evaluated and captured this real technology that we were able to consider. This is Tornetic from Germany, and we were able to achieve the performance with the design, as you see here. And we were able also to achieve the control, where we have the RCA, which is a resilience control architecture that allowed us to achieve multiple controllers. So we have multiple flywheels, multiple battery, multiple ultra capacitor, and we were able to integrate those with the integration with the grid, with the integration with different industries. So those are different applications, not only for fast charging station. Fast charging station was actually one application, but we actually implemented this with substation, and it was very successful. We demonstrated that actually the substation can achieve high performance and reduced cost as well. In addition, we achieved that we are able to implement the fast charging station even with industrial facilities, and this was actually quite promising, and we demonstrated that in one of our project evaluation. And we showed that it is possible to be implemented with large scale industrial facilities to achieve high performance and manage the peak, manage the transient analysis, and manage a high load with reduced cost as well. In terms of operation strategies, we implemented a number of scenarios, such as number of cars in the station, vehicles to DC bus, DC bus to vehicle, battery storage to the bus, the DC bus, or DC bus to the battery storage. And we have done actually a number of combinations. Those just examples, but we did the really larger amount of combinations, including the flywheel, the ultra capacitor, and combined with the battery, with the renewable portion, where we have the PV, the wind, as well as the nuclear power plant as SMR. In terms of control architecture, we actually implemented interesting and integrated control architecture, where we are able to show optimized performance with supervisory control, optimization control, configuration control, protection control, power management, demand-side management, power electronics control, and self-healing control. And we implemented this as integrated with the whole station. As you see here, this yellow line, that is actually emulator. So in the lab, we actually had a PV with DCD, programmable DC source, and we had the battery bank, we have supercapacitor, and the flywheel. We implemented that as emulator. We used Opal RT as real-time simulator, and we implemented our energy management, where the charging meter and the charging portion with the electric vehicle and the bus is able to implement the interface with the back end, which is the fast charging with renewable energy. This was actually implemented with the flywheel and published the work in a number of publications. And we implemented the flywheel model. We implemented the modeling portion of the flywheel, and we developed and evaluated and optimized the performance, including the rotor speed and the energy stored in the flywheel with discharging time, to ensure that we are achieving the highest possible charging performance as well. We implemented the hybrid energy storage that include the flywheel energy storage as well as the battery energy storage. So we integrated them together to achieve the high performance battery, and we implemented the model, and we integrated also with intelligent control. In this intelligent control, we used MRAC, which is Model Reference Adaptive Control. It is one element that allowed us with energy management scheme to integrate the whole fast charging to maximize the profit, maximize the performance, maximize the lifetime of the battery, and also maximize the performance of charging, which is charging time for electric bus, truck, or bus or truck. And we were able to achieve that performance and we were able to demonstrate our elements. So we actually developed that program, and we implemented the code, and we demonstrated that the performance is actually achieved. So we were able to see the load, the power, and MMR, which is a small or micro modular reactor, the PV, the wind, and the energy storage. And we were able to demonstrate the performance. For example, here we will show that our the conventional versus the EMS, we were able to achieve the performance enhanced. For example, here, this is shows the electric vehicle and the performance from the electric vehicle or the electric bus. And you see here, this is, we achieved, I'm showing here, this achieved for 12 minutes to reach from 20 to 80 SOC, and for the B, for the bus, from 17 minutes from 20 to 80 SOC, based on our design. So we were able to achieve high performance based on our design. This is very interesting and very crucial for the deployment of the fast charging station. And this, of course, this is based on our design. However, the design itself can change, and we are able to change the design based on the requirements. And this is one of the benefits of our model. In addition, actually, what I would like to emphasize that we were able to extend the design to become hybrid energy, hybrid fast charging station, and that includes the hydrogen as a charging for fuel cell, as well as the internal combustion IC and the diesel, as well as the electric vehicle. So we were able to demonstrate the hybrid energy fast charging station, not only as electric vehicle with wireless or wired for electric vehicle, but we are able to integrate, and we build a model, and I will explain how this could be crucial for electric bus, electric truck, and rail, or even both. And we implemented the picture here to show that our system with controllers, with nuclear renewable hybrid energy system could be implemented in a very effective way. And this actually a key findings of our project to demonstrate that we are able to install and deploy hybrid charging station in existing infrastructures. In addition, I introduced the concept of transactive energy and transactive mobility. This is very crucial, and while we are analyzing the design, the configuration, the control, I found that it's possible to also optimize the cost and the profit for the owners and investors of the fast charging station. So in this picture, where we have the fuel cell, the PV, the wind, the grid, the nuclear reactor, which is SMR, could be MMR, the ultracapacitor battery and flywheel, we implemented the electronics with the agent connection. We were able to demonstrate that actually with the mutual communication between the bus, if you see here, this is the TEMS, which is the truck energy management, the BMS, the bus energy management, the VM, the vehicle energy management, as well as this is from the vehicle side or the truck side or the bus side. This is connected to the station side, -S. So here is the -S, and then we have our AFCS energy management system, and that is integrated with RT-COS, which is real-time co-simulation with Opal RT and user interface, which means that as an investor, I will be able to monitor this station, and I will be able to negotiate the price and increase the profit. If I am investing in the wind turbine only, or the PV, or the nuclear reactor, I will be able to increase our investment and any of these components. This is a model that could be enhanced and implemented as one of the commercialization that we are offering, although it is outside the project, but it is actually, I'm proposing to be an extension of the project to show commercialization plan for and investment plan in the energy and transportation electrification infrastructure. In terms of applications, as I mentioned, it is very crucial and it is very useful to be implemented as part of the substation. Could be for a small community, could be for rail and for buses and for the grid in total. Also, we are able to integrate this in different levels with different scale, and this is what we are offering really to be possible for industry, rail, marine, and I had actually a project with transportation electrification for fast charging for electric boat and electric marine, as well as for trucks and bus and industrial facilities. And as this is the whole picture of the whole integrated. And finally, we actually implemented this in the lab. So this is our demonstration. This is our first model. And then we translated everything into electronics. So I just show you these electronics. We implemented this with dual control. One is embedded programmable control and one PLC, and one is embedded control with Arduino, Raspberry Pi, and so on. So we were able to demonstrate the system. I will be very pleased to take any question, and also would like to share with you one of our publications. So this is one of the books that I published with Elsevier, Smart Energy Grid Engineering. I also published another book with energy conservation in residential, commercial, and industrial facilities. And the last book, which is just published a few months back, Fast Charging and Resilient Transportation Infrastructures in Smart Cities with Springer. I encourage you to read this book. It has all of our designs and the performance and integration and implementation and deployment strategies. I would like to thank you. And this is our conference. It's running from 13 to 15. And I hope that you will enjoy the conference next year as well, as this year you might not be able to attend it, you did not attend it. And I would like to also refer to our publications. And thank you very much. And I would be happy to take any question.
Perfect. So that was the presentation from Dr. Hussain. Now I would like to introduce and welcome Monsoon Fu, who is the Director of Product and Innovation at eCamion. And over to you, Monsoon.
Hi, everyone. Hi, thank you very much for the introduction, Rachid. First of all, I'd like to thank QTRIC for letting us present in this conference, and also we would also like to thank Purchase Support for the project we've worked with. We worked with QTRIC on this development of next generation battery integrated EV charging stations. Next page, please. Yeah, so a bit of introduction. So Joule is a trademark brand by eCamion for EV charging and transit charging businesses. We are based in Toronto, but we have branches in the United States. In the United States, we have been we are end-to-end solution providers. So we actually design, develop, manufacture, and deploy the charging station all by ourselves. We have deployment from literally from end to end. Across Canada and USA, we have deployment in Alaska, as north as Alaska and as south as Florida. We also have a lot of deployment in Canada, such as in Alberta, Manitoba, Ontario, and we also branching into New York, California, and Michigan territories. eCamion is determined to deliver a green future. We are also very focused on optimize and digitize the future to lower the overhead of environmental, social, and government and governance overhead. We also 100% support of manufacturing in Canada. In fact, we firmly believe that manufacturing is one of the best industry to integrate individuals, everybody from different background and skill set into the general economy. And in this presentation, I will be focused on the practical use case of transit charging with battery. Next, please. So for now, we do have 2 active projects. One with the Edmonton Transit Services in Alberta. So what we're doing, we're actually installing a large format station energy storage system to help them increase the utilization of their pantograph infrastructure. The second project, we're working with Durham Region Transit and Oshawa PUC in Ontario. That one, we're working on a 150 kilowatt power DC microgrid-based charging solution. Next page, please. So before we start looking into the solution, let's take a step back and look at the problems we're facing today. If we were to categorize it, we mostly have 4 areas from 3 different areas of the chain. So what we have is production of energy and power, delivery of energy and power, and the consumption. So at the production level, we do believe that there's possibly enough capacity in the plant, but it's the power that we have to deliver to this. It's a speed of reaction that we have to respond to when we're delivering high power into the e-transit, to respond to the demand of transit charging. The second area is the delivery. So we this with any deliveries, it always be the last mile delivery. How we actually bring the power from the generators to the buses. And the last one is the consumption at the buses. The buses are evolving. There are multiple standards such as from J1772 CCS to J3105-123, the pantograph. We're now talking about J3400, which is NACS. In the future, there's also one more coming up, is J3271, which is megawatt charging. The standards evolving. Basically, so now all these three areas are translating into four problems. Number one, insufficient structure. Is do we have enough copper, literally copper, to deliver the energy from the generation to the buses, to the transit systems? Number two is demand charges. Because we don't have as much infrastructure, because we are still in today's power network, we still have to use whatever we generate almost instantaneously. There's no buffer, there's no storage. We have been focused so much on the capacity of the grid, but not the flexibility of the grid. We are running a lot of peaker plants, which translate to a lot of greenhouse gases production, and also a lot of operation costs, material costs, which further translate to demand charges. The last one is utilization uncertainty, because the infrastructure may not be there, because there's a lot of like overhead costs, a lot of demand charges. There's deliberate downtime of the hardware, which means it's not economic to run the system. The last one is technology obsolescence. As we mentioned, the bus battery is getting bigger and bigger. Everyone's looking to possibly a different port. And also we look at higher charging power. The moment we install the hardware today, there's a possibility it will become obsolete very soon. These are the four problems we're trying to address as we go into the project. And in the next page, I will explain the goals, which is, as we said, we want to reduce infrastructure upgrades. We can optimize, add battery in the middle as a buffer, utilize the concept of simultaneous rate and duty cycle to put the optimal amount of hardware infrastructure upgrade into the project. Second thing is demand charge mitigation. Add flexibility into the application. Do not penalize the transit network on demand charges. The last one is operational stability. Use battery for such as emergency power supply. What if there's an outage? Or what if all of a sudden the facility has additional load in the hot day? The last one is versatility and future proof. Make the system modular. If there's a technological change, we're still package to protect. We're not changing everything. We're not redoing everything. We're just changing a part of the application to fulfill a future change. Next, please. So basically, what we give is our ecosystem considers a lot of things. Number one is transit compatibility. So we are working with a lot of bus manufacturers, a lot of transit networks, gather their feedback, and test with the actual equipment to verify the compatibility. Next, the second thing is on the edge AI. Hardware is one thing, but the operation is another thing. We would love to a lot of things, coordination between the hardware. So such as real-time adaptive power balancing, the value use of battery partitioning, such as you have a battery there. It's not just for transit charging. If there's no buses charging, the energy can also be used better to support the facility. Also we have automatic protection on the edge, AI responding to alerts and alarming. And we also each hub is also further integrated to our cloud system to form a network of hubs. And in terms of hardware, the third layer, what we have is energy storage battery. It's proprietary. The battery we design and manufacture everything except for the cells. So we buy the cells, we put them together. We even develop a hardware and firmware of the BMS by ourselves. In terms of power electronics, we have modular power electronics. As you can see on this illustration, we have provided a split system between the power electronics and the interface. So number three, the cabinet holds all the battery and the DC-DC power converters and the AC to DC PCS, whereas one is just the interface. It doesn't matter what we attach. It can be J3105-123. It can be a plug-in port. It can even be the further megawatt charging J3271 if it were to come out in the future. In addition to that, we have preventative fire suppression system inside the cabinet to even exceed the requirement for UL 9540A. A lot of battery today, they respond to the fire at the accident. We actually put AI into it to predict when the accident may happen, and we prevent the fire suppression to stop at the very early stage to mitigate the possibility for thermal runaway, because we all understand in battery technology when thermal runaway happens, there's very little we can do but to keep splashing water to cool down. The temperature inside can go to as high as 13 to 1800 degrees Celsius. And the last one is the last key part we have is DC coupling microgrid. This is probably, I would say, that the innovation that came in over here, especially in this project, is we would like to isolate the hardware from the grid. Typically, a lot of charging stations today, you've seen some of them have a battery, but they're all connected, all commonized, integrated on the AC side of the grid. This makes the application binary, which means to prevent backfeed, they're relying on a backfeed preventer. If the net energy into the grid surpasses a threshold, the entire site will be cut off. Whereas in our case, we aggregate everything on a DC bus designed by us, and then we use the PCS as an active control gateway for the interaction between the grid and the DC microgrid. Next page. So this is an illustration of what we are providing. So basically, traditionally generic fast chargers or traditional bus chargers, you consume whatever. You generally have to take all the power have to come from the grid. This would result in a lot of infrastructure upgrade, not just at the very last transformer. So in some cases that we have projects, they even have to go up to substation level, which requires the construction of new substation. This will do two things. Number one, a lot of capex. Number two, a lot of delay in the implementation. What we're trying to do is use battery as in the middle. We trickle charge the battery because we know that we don't have to charge the buses 24/7. So whatever the bus is not charging, the battery will be there to store the energy. This is why we say simultaneous rate and duty cycle is important. This also allows the flexibility for installation, especially for en route charging. Today, a lot of charging are depot charging. They're centralized because of reason number on the line above, infrastructure upgrade. Whereas if we put battery in the middle, we start all of a sudden we will sort of lose up the requirement for the site, and we can have en route chargings. We can even prolong the route for each bus line. Next, please. As we said, we provide an integrated end-to-end solution. We have the chargers, which are just interface into any vehicle. It can be a plug-in, it can be a pantograph, it can be a megawatt charging port, which is a triangle port. We have the hub. We host every power electronics and battery, in a separate cabinet. We keep them away from the operator in a safe distance. And the last one is the link. We not only provide the hardware, we also provide a fully digitized solution. We're including a cloud portal so that the operator have complete visibility of the hardware and the management of its energy within. Next, please. These are the two solutions we'll currently provide to potential customer and transit collaborators. We provide a plugin because we understand a lot of transit networks. They are still on the planning stage, still in the prototype stage. They want to have the minimal trials and then get used to the system. We also have the pantograph and we can do, and we work with a couple of suppliers from Europe, so we can do J7, 18, 35, 1, 2, 3, either way. And the hardware, as we mentioned, we use split systems, so the hardware in the cabinet are the same. It's just a matter of time on the front interface. If a bus operator started a trial with a Joule 150 interface, they can always upgrade the system into the pantograph solution. Next, please. This is another page. There's another I call this marking page. The solution, the standard configuration we provide. So we in this case we allow the customer to configure their battery size and the amount of power electronic DC converter modules we have in each hub to fulfill their need. And because we provide a cabinet, we have a space to package protect future upgrade. In this case, we can minimize their future capex for the retrofit. Next, please. As we mentioned, these are the three different building tech blocks we have. We have our own power core, 75 kilowatt each. The battery modules, they come in 13.5 kilowatt per module, and we often put 16 to 18 in series to form a string. And we can also put multiple strings in parallel. The last one is as an example is the three. We can go up to even 300 kilowatt. And once the megawatt charging is coming out, we are active on the console. We also implement that. Next page. And this is the microgrid illustration of the microgrid, DC microgrid we are creating. We mostly integrate everything on the DC bus. We build the aggregation panel by ourselves. We have control gateway to each power source, including the grid and the solar panels. We're also exploring one very interesting application today is the getting power from the third rail. A lot of metropolitan transit network, they already have a third rail with their subway systems, and they don't run the subway in the middle of the night. So they already have this infrastructure, and we are creating a microgrid that can be isolated from the source through a controlled gateway. We can also try to use the existing infrastructure like that, such as a third rail, to minimize their future spending on the upgrade or bring in power. Next, please. And on top of that, this is also a feature that probably only us are providing. So we do have fully digitization. We actually have a lot of API that can be tied into building management systems and even cloud. We even have support OpenADR to get direct connection to the utilities to respond to certain events. Such in California, we can possibly respond to our emergency load reduction, just like GA, that's a global adjustment, just like what we have in Ontario. In this case, we not only provide visibility of the equipment state of health, but also diagnostics. We also have smart management features to help the user mitigate their overhead in operating this bus charging solution. Next, please. Just for everybody's benefit, we are on the OC Open Charger Alliance net. We have OCP 2.0, which means we're not tied to our own network. If someone were to use a third-party provider, already have a third-party provider, as long as they're OCPP 2.0 compliant, we can also pipe in the charger information into that platform. Next, please. And this is a summary of what I presented. It means we are end-to-end solution provider. One of the biggest problems I've observed in the e-bus and even EV charging industry is it's been discrete. Everyone has been a discrete player in the market. The upstream often pass down to some of the hidden costs to the downstream players, but we provide a full solution. This is a great way to increase the rate of the adoption and the accelerated adoption process. Next, please. This is the one last thing is the future. We believe in the future there will be a hybrid model. There will be depot charging where the bus be centralized and charged mostly for overnight when there's no active services. But there should also be en route charging everywhere. That's what we're trying to do with Durham Regional Transit. En route charging enables the utilization rate of the bus. It allows the bus to go for a longer route. I think this is also been further proved by some other bus charging solution providers in Europe. Thank you. And next page, please. That's everything. Yeah. So all in all, we would love to bring more. We would like to offer a solution that can bring grid resiliency. Its modular design is packaging protect for the future. It allows renewable integration. And the last one is because we build everything here, we support the local economy. We're creating jobs in the sustainable technology sector in Ontario, not just in software, not just in tech development, but also manufacturing and its associated business. Thank you. I think this is the last page. Yeah, thank you.
So thank you, Monson. I think that was a really insightful presentation that you gave. It's kind of given me a couple of questions as well to ask. So I think let's just open the floor for questions. We have Dr. Hussain has joined us as well. So
No problem.
Let's start with the question and answers. So I have a couple of questions already with me here. So let's start with the first one. So it's to the both of you. In terms of funding, in which areas should the government funding be directed to enable smarter vehicles and transit decarbonization? I'd like to hear your views on that.
Yeah, so in general, we think there are a few areas. Number one is definitely the hardware. Right now, a lot of hardware is coming from overseas, and also, which means not referring to manufacturing, but I'm referring to compatibility. Today, one of the biggest problems we face is when we're trying to develop the charger. Developing the charger is one thing, make it working with the vehicle is another thing. So what we had was for EV charging, there's a few companies providing a commonized test platform. It's ATS systems. So they simulate the real car. They actually work with OEMs to create a car communication profiles, car characters, and use an automatic test emulated load bank to simulate the profile operation. So once we plug in, we know if the controller is working well, is compatible with this OEM or not. This kind of technology is not there for eTransit, because eTransit, instead of going through a hardwire line, they actually go through Wi-Fi communication, and that's the biggest problem here, because we can make the charger, but we have to keep getting buses in whenever there's a new models from different manufacturers to verify the compatibility. That's definitely number one. Number two is regarding the software, especially AI. I'm not trying to use the big name, but I'm really referring to it because think this way. In the past, we're mostly familiar with the gasoline. The power density of the gasoline versus EV charging per minute is different. Period. So gasoline probably fill up the buses in 5 to 10 minutes. EV charging with e-bus charging, it will have to be 15 to 25 minutes. So which means, and a lot of these will be automated and manned. Which means we do have to invest in software to automate the process, reduce the overhead of operation. Yeah, that will be the two areas I'll be suggesting. Last one is just keep investing in the hardware. The standards are evolving, the need of the market are evolving. 2018, when I first started working EV charging, everyone thought 50 kilowatt was really fast. Today, we're even surpassed CCS 300, 500 kilowatt. I'm on the console for megawatt charging. We're talking about 1 megawatt. And per port, which is amazing, but also requires a lot of R&D, a lot of testing, a lot of advanced manufacturing to actually make it come into a reality.
Perfect. I completely echo by your thought where you say that back in 2017, when I also joined, I think 50 kilowatt was like the fastest we could do. And you're absolutely right. The megawatt standard is something which everyone's working on. In fact, we just did a recent pilot for megawatt testing in Europe as well. So that is something which we're all excited about. That's going to be huge, at least on the trucking side of the business. So for the for the transit application is something which you'll have to look at it. But for the trucking side of the business, that's going to be huge. Dr. Hussain, your views on the question.
Thank you. I guess quickly, two things which I feel quite important is the first one, when we talk about the smarter vehicles, we would like to implement more infrastructures that can accommodate for charging with different technologies, where we have the the wires, wireless, V2V, the charging infrastructure is important. So that's where I felt a lot of gaps here. In terms of the other part, which is the energy management, which is the transactive portion, which is the investment. I believe that smarter people will not feel it unless they feel more profit and more benefits out of it. So I think investment model that can be linked with the transactive mobility and transactive energy around the charging infrastructures. The last piece, which is actually like more into, I would say the traffic, the smarter traffics. We understand that the braking and traffic management will lead to longer life, better traffic, better mobility, and the traffic itself and the smarter traffic signals is important to cope towards autonomous vehicles, but autonomous transportation. But I believe that traffic signals and traffic infrastructures will require a lot of attention, and there are a lot of potential ways to really improve the traffic signal. So those, in summary, I feel could be a potential area. Thank you.
Yeah. And one last thing I think I can mention is probably the people, general public education, also the expertise. As we mentioned, that as for any technology to become the picture, there's always a learning curve, a learning period. And as we think about cell phone, when we were all using Nokia, when the Motorola cell phones, I'm not saying the brand, but there are the charging habit definitely from how we use with smartphones. Also, manufacturing is also different. So we're not talking about level 2 chargers, and we're talking about the power electronics that they're going to develop or infrastructure they're going to deliver at the charging for very high power or very high, extremely high power. If the manufacturing process is not there, we don't use advanced manufacturing skills, make them right. The reliability is going to become a concern. When reliability becomes a concern, the adoption will definitely become an associated concern.
Perfect. So we've heard both sides on those different views that they've had for the question. I'll move on to the next one. The next question is, I think it's I'll say, if not $1 billion, at least a multi-million-dollar question. How do we reduce the cost and speed up the implementation of the fast chargers?
If I may answer first, I would say number one is look at the big picture. One of the biggest concern I have with today's implementation process, everyone's so discrete. The charger, a lot of manufacturers, they manufacture just a charger. They leave the integration problem to the downstream client, and when that happens, there's a lot of like delay because of overhead. And the second thing is educate, because the general education is not there. Everyone thinks, oh, all I need is a charger. Because on paper that does work, because on paper a charger is definitely cheaper than a charger plus a battery. We can't deny that fact. So we have to look things in the holistic picture. What's the optimized infrastructure? I give a personal example is we do have a potential customer up north in Paris. One of the biggest problem is they have the capacity, but they have to run the line under the highway. This is economically unfeasible. And the moment they understand that they're only using that line 25% of the time, 25% of the day, less than 25% of the day, they're like, why bother? So, but if we look into not just the capacity, but the flexibility, and including what happened at the operation, which is smart energy management afterwards, then the picture, then everything can be easier. Because at the end of the day, for any bus operator, it's end to end. It's at the end, it's operation. It doesn't stop at the charging station installation. Doesn't stop at the facility upgrade. It's at the end is operation.
Perfect, Martin. I'll have to ask you to hold your thought. I have to move to Dr. Hossain for his thoughts as well, because we're running very close on time.
Yes, thank you. I think cost is really the most important, I would say, key success factor, and the KPI. I see question in the chat is also how could you please elaborate on KPIs for evaluating the fast charging? Of course, in general, the response or the performance has different layers. One of them is the cost, and the second is more into environment.
And the third eventually will be related to safety, reliability, and some other elements related to like socio-techno-economic analysis with social aspects of it. But of course, the mobility. For instance, but coming back to the question, so those are about the KPIs, but coming back to the cost. In fact, when we look to the cost of implementing fast chargers or charging stations in general, the costs are primary things related to the vehicle itself, how the readiness of the battery and the electronics around the vehicle, and we have the component around the fast charging, and the area which is the communication between the vehicle and the charging. And so that is like in general to implement a solution between the vehicle and the charging. So the charging station itself, the design, the controller, the electronics, the software portion of it, those are aspects in addition to the security as well. Now, how to reduce the cost? Eventually, we have to tackle each of these elements, but the most difficult part, I believe, or the most important part is the fast charging stations, where we believe that there are a lot of potentials to improve the fast charging station in terms of performance related to cost reduction by introducing more into hybrid energy systems that will reduce the cost from the grid, improve the reliability and the impact on the grid, improve also the inertia and the potential supply to the charging station. For instance, we evaluated the flywheel and ultracapacitor and some hybrid energy systems to complement the grid to accommodate for high inertia and high potential to implement better electronics for the charging infrastructure. Those are elements I believe could lead to a better performance. The second piece, which is exactly like related to the vehicle to the charging station, which is the investment and transactive energy. I strongly believe, but after talking to many players, stakeholders in the project, from investors to charging technology providers to utility to charging station owners, I felt that the transactive energy portion and the ability to translate the investment model into profitable win-win-win situation is crucial, and that will enable all players to actually get the profit on the table, and that could be translated into like transactive energy that will allow the utility to have a better model to charge for the charging supply. The investors of technology providers in the station will get the opportunity to get investment and reward around the charging infrastructure, and the vehicle will be able to select the cheapest option to charge their vehicle in terms of the distance and the range requirements. So I think those could be potential to reduce the cost. Thank you.
Perfect. Thank you so very much. Just one quick question. I will give 30 seconds to the both of you to answer that one. What are some of the biggest challenges ahead for us for optimization of e-buses? 30 seconds. We'll start off with you, Doctor.
Okay, I think optimization is AI. Optimization is design optimization, smarter design of the electronics and smart apps that will allow the buses to communicate better with the station. Thank you.
Perfect. Monsoon, over to you.
I would say I read the same as number one is looking at a smarter optimization. Don't look at discrete building block. Look at the big picture, the entire infrastructure plan, end to end, from design of hardware to manufacturing and to the software support and operation. And very last end is the people. That's my solution.
Perfect. Thank you, the both of you, for those lovely presentations and those insightful comments that we had. Unfortunately, we had a few more questions, but we are running out of time, and we've already eaten up 3 minutes out of the 10-minute break that we had. So I will pass it over to Vincent to take it forward.
Sorry about that. That was dumb. I was muted. Thank you to our first two speakers. And before we go to break, we have another sponsorship commercial from NFI.
Lighter, longer range, better energy recovery, and smart city capable. Our most advanced electric bus just got better. Introducing the Excelsior Charge NG, our next generation battery electric zero emission bus. Safely carrying more passengers for a longer range, the Excelsior Charge NG delivers new high-performing technologies, including a new lightweight traction drive system with up to 90% energy recovery, next-generation high-energy batteries that extend range up to 13%, and advanced protective battery packaging designed for easy install and streamlined maintenance. With simplified design and better system durability, the Excelsior Charge NG offers a high-performance bus that's more sustainable and easier to operate and maintain. With uncompromising quality, fewer parts, and more recyclable components. This is how we're driving the new mobility era. This is the Excelsior Charge NG from New Flyer.
Okay, so thank you to New Flyer NFI, and let's go to our break now, and we'll see you back at 3:15 promptly. Thank you. Okay, everyone, I think we're ready to start. So I'd like to turn things over back to Rashid again for our session B of today's webinar, meeting and managing the demand, grid management and charging schedules for electrified transit systems on a national view. Rashid, you ready?
Yes, I am. Thank you.
Okay, go ahead.
Perfect. So now we had an interesting first session. Now it's time for the session B. And for this, I would like to invite Dr. Javed Ibrahim to take over and present his presentation. Dr. Javed, over to you.
Hi, everyone. I'm Javed Ibrahimi from Queen's University. Let me share my screen and start my presentation. We have done a research project with Qutric from 2019 to 2021, and our research methodology was focusing on the mainly powertrain of an electric bus, and in detail the DC to AC converter. For each our powertrain system, we need a conversion system, which is a power electronic circuit, which convert electricity from batteries to the electric motor, and in the some operating mode from motor to battery system. We follow this research methodologies for our proposed solution for a new power electronic system for an energy conversion in electric bus. As you know, for each conversion system in electric vehicle, we need a DC to DC converter to provide a proper DC link to the inverter, and using the inverter, this energy convert to the electric motor. This is a typical powertrain of an electric vehicle, which is actually the Toyota Prius. For the DC to DC converter, one important point is that the high power requirement for the system. So one of the initial ideas to reduce the size of the DC to DC converter is process the power, some part of the power from different way. Actually, we can use a DC to DC converter, low power, to convert a lower part of the energy from battery to the inverter. And using a multi-source inverter, we can directly connect the battery pack to the inverter and as one of the input, and the second input is the output of the DC to DC converter. And using this system, we can reduce the size of the DC to DC converter. Our proposed topology is the combination of an ultra capacitor and a battery pack as the input of the multi-source converter, because when we have a multi-source converter, we can reduce the size of the DC to DC converter, and in addition to that, we can use one of the input source as additional source like ultra capacitor. This is our proposed topology, which is consists of the DC to DC converter for converting energy from a battery pack and a supercapacitor as an additional energy source for the electric vehicle. And using this structure, we can combine these two sources of energy, and in different operating mode, we can manage the power between these two sources. And as we can see, the efficiency of the system will be improved considerably. We have the different operating mode as shown here, using the different switching state of the left side of the converter. And in each mode, one or both of two the sources are engaged in the power processing system. We propose a modulation scheme and a specific modulation scheme to combine the 3D operating mode and provide us flexibility to manage the power between these energy sources. There are some details of the operation of this converter at different operating mode. For each converter system, we need an controller scheme. The controller scheme should be combined with the modulation scheme, and the modulation scheme provides the switching state. We have implemented a specific controller scheme for this converter. For each operating mode, we have actually 3 operating mode in the motor operation mode, and 2 operating mode for the regenerative mode. And the power flow of the controller strategy implemented to provide the SOC of the battery and ultra capacitor at a specific range. We compare our proposed topology with the state-of-the-art systems, which are actually the NPC-based converter, T-type based, and the configurable multi-source inverter. Our proposed solution provide lower number of switching devices for the energy conversion system with the same number of DC sources and operating mode. at different operating mode, the losses of the proposed solution is reduced, and because of that, we have improved efficiency at all operating mode for the system. The simulation results are presented here at mode 1, which modulation index is low, and the motor operated at lower output current. But by increasing the reference current, the controls goes from mode 1 to mode 2, and in this mode 1, the battery is engaged, and in mode 2, the battery and the ultracapacitor, both of them are engaged to provide power to the output. And in mode 3, only the high voltage battery pack is connected to the inverter. To evaluate our system at a standard driving cycle, we implemented this system at EC15 driving cycle. We have a different speed for motor during a specific time period with different load, and by changing the speed and the load, the operating mode accordingly change from 1 to 4, and the SOC of the battery system and ultracapacitor remain at specific values, and they're properly managed to provide power to the output. We have implemented the system experimentally at ePower Lab. We have some different parts: the AC current sensor, DC voltage sensor, gate driver for the system, and a signal conditioning board. We use a specific DSP to provide the gating signal for the switching devices. And here is the low scale down power board, and the setup for the battery ultracapacitor energy storage system is implemented, and there are some experimental results: lane-to-lane voltage, load current, and DC source currents at different operating mode. And in mode 1, only the battery pack is involved. In mode 2, battery and energy and ultracapacitor, which is energy storage system, is involved. And at mode 3, only the high voltage battery pack is involved to provide load currents. And as a conclusion, we provide a specific DC to AC conversion system, which provides us with higher efficiency. We can use different energy sources like a battery pack and ultracapacitor, and by managing this multiple source of energies, we can provide better efficiency during drive cycle. The comparison with the other present topologies show the higher efficiency of the proposed solution, and we implemented this system in the ePower Lab, and the experimental results shows the capability of the proposed solution. Thank you so much for your attention, and I'm ready to answer your question.
Thank you, Dr. Javed, for the presentation. Now I would like to request Dr. Sarah Diamond to come on and present her slides as well. Sarah, over to you.
Yes, hi. It's just a pleasure to be here today as a long-term member of QTRIC and to have this opportunity to present our research. And I really want to thank my long-term collaborator, Jeremy Bowes, the QTRIC team, the Government of Ontario, Mitacs, Social Science and Humanities Council of Canada, and Infrastructure Canada for their support. We'll go to the next slide. So our plan in our research was to provide visualization analysis of e-bus routes in facilities projects using dynamic visual analytics tools and also design science, so understanding the perceptual tools of visualization and also how to interpret the data effectively. And our goal was to support electric bus implementation in Canada and to further research within the QTRIC project and amongst its partners. Next slide. So our goal was to provide, as I mentioned, visual analysis. And we can see here what our research focus was. So we had a series of questions. How can we integrate two-dimensional and three-dimensional visualization? So by that, I mean graphs of various kinds, but also immersive and really high-quality mapping strategies. And you'll see some of how we took this forward into a meaningful visualization system and use this to prototype e-bus routes and changes in those routes and the impacts of charging, etc. And then what cartographic approaches. So here we do mean what kind of mapping strategy should we use to support analysis of scalable and dynamic data. We were looking at energy optimization, very appropriate for the conversation we're having today. So looking at optimization and efficiency and how we visualize that, and then what kind of additional insights, such as GHG levels and reduction, could we look at, and then what kinds of tools. So we worked very closely in the latter part of our research with the QTRIC team, who of course are very proficient in using various AI solutions for their analytics. And, foremost is a user-centric visual framework. So how do we really think about our users? And I'll talk about that as we move through the slides. But, our partners who are QTRIC members, of course, are very critical for this. So we'll go to the next slide. Thank you. So how did we approach the research? Well, pretty rigorous literature review. We're not going to subject you to that at the end of our presentation, but we looked at road and rail transportation, sensor analytics, predictive and prescriptive data insights, various ways of discussing and representing energy efficiency, and of course spatial analytics, including GIS and cartography and our field, which is visual analytics. We had a look at the kinds of data that were relevant to the work that QTRIC and its members were undertaking, and look at the kind of variables we would visualize, and then understand visualization tasks. So, what people using these tools would need to do on really almost a minute task by task basis. So we built a series of personas that, represented the kinds of users that were relevant for the system. On to the next slide. Great, thank you. So we did, of course, do case study research. We looked at some of the best practices. Shenzhen, China is very interesting, hugely ambitious implementation of 16,000 electric buses. They could collect data from an iCard system, and they would be able to, correlate locations, passenger trips, and demand. So passenger flows, optimization, and electrification routes and priorities there. Next slide. A second important case study is READY's key performance indicators for New York City's route optimization. So this was very much looking at, how to serve passengers better. This was not so much looking at issues of electrification, but passenger service and distribution. Of course, we want to optimize that as we bring in e-buses as well. I'll talk about that later. On to the next slide, and thank you. And then looking at some of the best practice within industry. So this is visualization of Winnipeg, their report on e-bus purchase costs that Siemens, for example, developed, including all of the different factors, including GHG emissions. So you'll see how this influences what we do. We'll go to the next slide. So some of the related work our lab does that we thought was important. We did a project with TTC and University of Toronto's transportation engineering folks. We're very close friends with them. We do a lot of work with them, which was looking at bus bridging. So essentially, you know what happens when subway lines go down and how can you use bus bridging effectively to do that? We'll go on to the next slide. So we put together a number of comparative visualizations for bus bridging scenarios. So this is really kind of looking at how you think about routes being bridged, points of traffic congestion, riders affected and delays. And we'll look at the next slide, which sort of culminates this research. There you go. And so you can kind of imagine a similar approach to managing BEB bus deployment and looking at load capacity and where there's intensive passenger interaction. And if you're adding things like just-in-time services or demand-based services, this is a kind of system that could be helpful. We'll go on to the next slide. And this is another related project. It's a tool we developed with iCity and Esri Canada and with my colleague, Dr. Eric Miller of U of T and his team. And it's an example of a criteria that we're including sort of transportation types from active to public transit, street widths, landscapes, and built space characteristics. So this is a tool that allows planners and engineers to look at how to achieve a complete community metric. So by actually moving sliders around and then eventually extrusion onto a 3D map, which we eventually built, you can see the ways that multivariate data set were placed against an index that measured the completeness of streets. On to the next. So we built prototypes for the QTRIC project. We consulted with a number of agencies, and some of you are actually on this call. I want to thank you very much. A number of companies who are part of the QTRIC membership, and through our SSHRC grant, we talked to a lot of power providers, technology companies, and agencies, and of course, a big thank you to QTRIC. So we'll go on to the next slide. So this example shows the ways that researchers and implementation teams can accurately track the progress and impacts of eBus implementation. So here we're essentially designing and prototyping 2D visualizations integrated with maps. So we always had this idea, and you'll see it maturing as we move through the prototypes, that what would be valuable for QTRIC would be to have a national map that would be able to really show in a deep and meaningful way the data across the country as e-buses were implemented, and then to be able to go into each city or town, or in some it's a rural transportation system, and look at all the factors of e-bus implementation there. So we'll go on to the next. And I'm not calling out our great interns and our aid designers, but their names are on the slides. So this is a further prototype. We're starting to look here at local, regional, and national maps for all provinces and cities in Canada that had an electric bus demonstration running in 2020. And QTRIC was using this data to be able to argue the value and the progress that was being made and where we needed additional federal, well, tri-level funding. And you can see the ways that we're looking at then having examples of specific cities and transit systems and being able to understand the level of implementation. So this is just a sort of snapshot. Onto the next slide. Here, it kind of gets more exciting. What we're doing here is we're really, it's a sketch. And it's a user-generated centered dashboard that would support implementation of electric buses in Canada. So what we're doing here is we're allowing the user, they've chosen a city, then they're able to see that city in detail. They can drill into the detail. We got fabulous feedback from the first iteration of the tool or the prototype, which was to add a color-coded route system that would be essential to read the tools map and include more comparative charts and graphs to help visualize the data more appropriately. So, average battery levels, daily use per rider, average bus temperature, delay performances per route. These are just examples. And again, you'll see these mature. We'll go to the next slide. And then here's another example. This is a dashboard prototype that we built using user interaction key information. So this would be times taken for routes and charge rates, which is the left image, and then the charging counts, nominal counts, and garage counts in the second image, which is on the right. And we'll go on to the next slide. So this led us to build the really next significant and final version of the prototype, which is a dynamic HTML dashboard that's coded with Mapbox GL and D3 and JS for data visualization. Qtrich was a fantastic partner in this. They asked that we use an open source tool. We do a lot of work with Esri's tools as well in our lab, but we went towards the open source solution. And we're just going to take you, we're not taking you to the interactive prototype. That is something that Qtrich does have, but we're giving more of a sort of generic overview of what we did. So we'll go to the next slide. So what we were doing here, and this sort of follows through, is a national map with all the Qtrich member cities from which the user can choose. The map will move to and zoom in between different cities based on the user selection. And after confirming the city choice, the user can click on the enter button, is taken to another web page, and then they can find all the analytics and visualizations specific to that city. Each city would be hosted on a separate site or dashboard for ease of data organization and user navigation. On to the next slide, thanks. So, this gives you a bit of a sense of on-map visualizations with simulation results for range analysis. So the idea is to have this interaction between, you can compare two different bus routes or two different cities even, and then you have these animated bus icons that run between the bus stops. On the bottom right corner of each map, there's icons that will take the user to GHG emissions analysis pages or electricity cost estimation pages. So we're just going to give you some examples here as we wind up of some of the visualization strategies. So slide 20. We developed the next slide. Sorry, we developed a set of icons for application on various graphs and to increase readability. We drew from information graphics and international representations. We tried to get sort of global ways of representing the data through these buses to find a common language. On to the next slide. And then this graph, this is one of two graphs that are related to charging, recovery time, and energy consumption outlined with charging metrics. The next slide, please. And then this graph represents failed and successful recovery trips. Recovery time proportionally for Saturday vehicles based on trip counts, just an example. So it shows the bus routes, the ones more suitable for opportunity charging versus the ones that are not. So red colors refer to the trips that fail to meet the 5-minute requirement, and blue colors refer to the trips that meet the 5-minute requirement successfully. Next slide. These are graphs related to charging, recovery time, and energy consumption outlined with charging metrics. And so it compares to buses, no diesel heater, and with diesel heater, weekdays, Saturdays, and Sundays, because we know that these are different energy consumption rates. On to the next slide. And this is a grouped bar chart displaying annual GHG emissions from electricity, and it compares emissions of one bus to another with light duty, medium duty, and heavy duty. And then our next final visualization slide is the electricity cost estimation page. So there's a series of graphs that visualize electricity costs for both diesel bus and electric buses. And here you can see diesel versus smart versus non-smart, diesel heater versus no diesel heater, and on to the next page. So just to sort of sum up here, why visualization? Well, municipal transit authorities do need practical tools to identify and visual changes in work process, labor skills, and transition requirements, to consider the number and costs of operators for ZEB implementation, given that more buses and short routes may be required, to model all labor costs, for example, into an economic analysis of implementation. There's a need for contextual data analysis and visualization beyond the immediate environment and cost benefits provided by current commercial systems. And visualization tools can help decision makers see the interactive system as a whole, so they can identify and quantify the impacts of electrification across environmental, economic, and social factors. Next slide. We're just winding up here. So this is our core team. Thank you very much to them. We were successful in a SSHRC and Infrastructure Canada Knowledge Mobilization Grant entitled Sustainable Development and Electrification of Transit. So with that grant, we looked at strategies in electrification that furthered health and social benefits and economic impacts, and looked at barriers and strengths. And we also looked at requirements for data and tools for Canada. It was an international survey. So that report's available on the OKEDU Research Office website, and it resulted in another output, which was recently published by Environment and Wiley Series in Sustainable Development. And we had a number of research outputs, including conference presentations and a number of papers and book chapters. And we'll just go to the next slide, which is our thank you. So again, to Mitex, to QTRIC, to SSHRC, to Infrastructure Canada, to, of course, to Ontario for their funding. And we thank our university. And that is it for me. Thank you.
Thank you, Doctor, for that amazing presentation. It was really insightful. And the way you went through the slides, I need to learn from that. That's a personal note for you, for myself, that's how you go through the presentations. Perfect. I think now it's time to get on to those questions that we have. So I'll start off with the first question that we have. It's the same question that we had for the first session as well. Again, Dr. Sarah, I'll start off with you. In terms of funding, in which areas should the government funding be directed to enable smarter vehicles and transit decarbonization?
So my answer comes from that report that we undertook, with QTRIC as a partner and with SSHRC and Infrastructure Canada funding. We talked to a lot of people, and we looked at a lot of international comparisons, and without question, approaching the electrification of transit within a systems analysis of transit needs and transformation is really important. And so, those two things have to be locked together. And we have a transit crisis in some cities in Canada. We need to look at how to continue to invest. The better the transit is, the quieter it is, the better electrification is, the different kinds of buses you can get out to small communities, more adoption and more benefit. Second, create long-term stable funding. This is like, yes, we know this, but I just have to say it, between all three levels of government, and QTRIC's been heroic in lobbying for this. Supporting ZEP adoption and minimizing the risk to transit agencies for doing that. So you need long-term patient capital, which is not always the case with electoral cycles. There should be tools that include direct subsidy as well as loans, and align investments in grid upgrades, which we're so talking about that earlier, and clean electricity with ZEB adoption. And I love Dr. Hussam Gaber's concept of transactive energy models being part of this. So I was, listening to the first session. And the final thing, I don't want to, go on and on, but in our analysis, we looked at cost benefit analyses from cleaner air, fewer emissions, equity and social benefits of rolling out electrification. And we think governments absolutely need to, and the social benefits of ridership, that they need to quantify these factors and include them in looking at the impact of electrification, because the return on investment is not immediate, as we know with capital investment, but it comes back in many other layers in terms of social and health benefits, and there's the data to prove that. So that's my answer to that question. More policy-based stuff, than actual change this or that.
No, you're absolutely right. That's one way of looking at the problems, and I think you've actually hit the hammer on the nail, from my point of view. So, Dr. Javed, your views on the question?
From my point of view, because our project was created with a hybrid energy research system, I think spending more on the new technologies for energy storage system could provide us with some benefits, because we can reduce the cost of the energy by utilizing multiple sources of energies, and so promoting new technologies and new energy storage system could be one of the areas that the government can be focused on that.
Perfect. Thank you very much. Thank you very much. The next question: how do we reduce cost and speed of implementation of fast chargers? I'll start with you, Dr. Javed.
From a technical point of view, in of it, which was the power electronic structure of the powertrain. I think utilization of wide bandgap devices could be reduce the cost of the power electronic system, because these devices can operate at a very high switching frequency. At that switching frequencies, we can reduce the size and the cost of the energy conversion system. This is one of the areas that many power electronic laboratories are working on.
Perfect. Dr. Sarah, your point of view?
Yeah, I think that's a great comment by my colleague. Again, looking at the sort of economic development side of things, it just seems that Canada has a really important opportunity to become a major player in the BEV, ZEV supply chain, both as a vehicle and components manufacturer, also in terms of mineral mining and that opportunity that are needed for battery. So if you look at it as a cycle, a sort of virtuous circle, I suppose, part of how we speed this up is by being able to have the capacity in the context of Canadian industry to meet all those points in the supply chain and address those. The other piece I would just, well, maybe I'll talk about it in the next question, but it's about talent management and talent creation, and that came up again in the last session, but I'll speak to that later.
Perfect. I think I echo with your statement that we have to go local and try and develop all the industry that we can here and try and minimize the cost there. Absolutely right. The next question: what are some of the biggest challenges ahead of us for optimization of e-buses? Dr. Sarah, I'll start with you.
Yeah, I did talk a little bit about this, but I will talk about talent development. I think what's very exciting is, in this series, we are seeing the quality of the research that's happening in Canadian universities, Ontario universities, and colleges. And, we need to make sure that's supported. I didn't say that in, my first intervention. And then also that there's support to help those students move into industry. And then there needs to be a lot of support within the industry itself as it exists to retrain people, to, look at effective, systems management, and to have that talent and capacity there. And that's one of the visualization projects, that we thought would also be maybe helpful for QTRIC and its members at one point, is just, I mentioned this, to look at those transitions. And then something that we just heard again and again in interviewing people was that it was just very difficult for agencies to choose technologies, that the need for standardization, to have trials and pilots. And again, QTRIC has done a great job with opportunities to pilot and consortium for trials, allows a well staged play, sort of strategy and play, and that's really critical for implementation. So I talked about I think the other policy factors before, but there's the grid, obviously, and we've been talking about that and modernizing it, and also making sure that as you're moving into electrification, you're not then burning more carbon on the other side. We have to really work holistically. And I think those are challenges. And the other thing we heard just interviewing people is that there's a need for stability and long-term investment and patient capital, because it takes time for a return on investment to come back from municipalities.
And absolutely. Like you earlier mentioned, that the return on investment comes in multiple layers. It's not just eventual money that will come to you, but the other benefits that it brings across to the entire society, I would say. Dr. Javed, your point of view there.
I think one of the biggest challenges, the reliability of the powertrain system, actually the power electronic system, because for the fast charger and high power converters, one of the challenges is the reliability of that system, because the lifetime of the switching devices and the other components will be reduced at a higher power level, and I think the reliability of the power system considered more in the new developed chargers, high power chargers, and other power energy conversion systems.
Perfect, perfect. I think we have time for one last question, and Dr. Sarah, that's for you. What kinds of data did you need to undertake the visualization mapping, and what are some of the challenges, opportunities for visualization research in this area?
Oh, thank you. That's just such a great question. I really appreciate it. So the thing about doing visualization is you need partners. So, you know, we're doing research in what's effective perceptually, what works in terms of usability, what's meaningful. But essentially, we're building visualizations, you know, for transit authorities and for companies that are their partners. So we need data, but we also need humans. And we need those humans to tell us what their needs are and to respond to the designs that we create. And we did have some of that great interaction through Qtrich, so thank you. Yeah, in terms of data, you know, I think you saw some of it. It's everything from, you know, route data, you know, looking at data on specific vehicle types, charging station data. So, you know, we're gathering the data from the sensor systems that companies are being able to pull together. In the kind of comparative work, it's transit, you know, systems, and also any kinds of planning data around implementation, numbers of vehicles, etc. So it's the vehicles, it's about them, it's the transit systems, it's the charging systems, it's the GHG data. And then there's the human data around, you know, population demand and change, because we should be doing this hand in hand with transit planning. In our in that report we looked at a lot of great data around health impacts, so impacts of health of air on air pollution and also noise pollution. And Transitions in California is a leader in doing that research. So moving forward, as I said, you know, modeling change in transitions in labor force demand and the cost of that, certainly taking the kind of mapping exercise we did with Qtrich and being able to take that across the country, city by city, and really build a national map would be wonderful. And then I think some of this, I should have mentioned that one of the things that came out of the last research we did is an analytic index. It doesn't have a huge visualization framework anymore, but it allows users to kind of do trade-offs between different kinds of metrics and data sets around when they're implementing sustainable transit. So long-winded answer, get me going on visualization. You cannot turn the switch off. I am sorry.
It seems like you love your data. You love your data with the kind of work that you do. It seems like that. So I think with this, we come to the end of both our sessions. I would like to thank Dr. Javed for his lovely presentation and Dr. Sarah for your insights on the policy. And also like to thank Qtrich for bringing us all on this platform and giving us the opportunity to share our thoughts and for learning. At least I learned a lot. I will be going back with a few notes that I've made, and I will be definitely reaching out to you guys for more questions from my side. Vincent, over to you. Vincent, I believe you're still on mute.
I have a habit of not unmuting myself. Sorry about that, everyone. I talk too much, that's why. I'd like to thank you, Rachid, for being a great moderator, and thank our Session B speakers. So before signing off, I think I'd like to show you this video. And so next slide, please. And so because I know you're all wanting to register promptly, in the chat is the link to the website. You've seen it a number of times. We sent a number of outreach emails. This is our 5th annual ZETM conference. It's occurring in Burlington, Ontario. It's centrally located, easy to get to by air, rail, and other public transit means. And it's right off the Queen Elizabeth Way. You'll see the latest technologies as well as opportunities, challenges, and solutions to the successful transition for Canada's public transport sector to zero emissions. Slides there. I'd like to thank you for participating today, and we look forward to seeing you at our next session focusing on the hydrogen space on September 12th and our 3rd session occurring on October 3rd. So with that, I'd like to conclude today's session and thank you all for attending.